explain the general multiplication rule, but I'm gonna wait till the end of class.
Okay. All right. But like I said, yes. I'll just mention one thing about that because of that problem that you sent me. Other than conditional probability that comes from a chart like this, well, in a sense, that one that you sent me about the songs is conditional, but you don't look at it in the same frame of mind as this. At least not that I can know how to explain it. But what you got to look at it is everything else in 4.3 is just the multiplication rule. You calculate your two probabilities, or three, it could be three, and then you just multiply them. Well, the thing about that one with the songs, as I remember it, was what's the probability of getting such and such an order? Well, when you pull one out of the four grouping, it was four artists, the probability is 1 over 4.
Yes.
But once you pick that first one, there's no longer that person up there now. Now there's only 3, but you're still going back up and pulling 1. So it's what we call dependency. It's that second pick is dependent upon what happened in the first pick. So that's why the denominator would change to 1 over 3.
Okay.
See, and then like I said, and it's really the same thing as this in a chart, because what you're saying when you use that word "given" that is a man is you're cutting out everything now to just men, and it does a very similar thing. It's just that you don't have to do the multiplication here.
Okay. See, let me just ask you this quick question, and then if it's let me just real quick. See how you have this on here? Is that basically when we have to do the 17.5 divided by 195 divided by 94 over 195? Is that basically what we're doing the multiplication rule for, or no?
Well,
when we solve this, because you know how we have to flip and all that, and then we have to multiply instead of divide, or no?
Well, I think you're probably onto something there. Because you are multiplying, and because of the fact that we're using those reciprocals, that's why we lose that, and that's why you really don't need to do it. Do that, go through all that unless you really, really want to.
Yeah.
Like I said, you can just basically, when it's in a chart or when the data is handed to you, you can just find out whatever follows that word "given," find out how many of those are, put them in the denominator. Then, and for the numerator, you find the confluence of the two and put that number in the numerator.
Okay.
But I don't think. I mean, I'm not really confident enough to say that that the reason why we're multiplying is because of the multiplication rule. Because I just don't see it like that. And it may be that I just don't understand it well enough, but that's why I kind of put this in a different category when we're talking about the word "given," even though the multiplication rule of that one we did with the songs is the same thing, because you have to have that second pick is conditioned upon what the first one was picked out.
Yes.
I mean, you got to pick that. So they're both conditional probability. It's just that, like I said, is this one, I don't know. I've always looked at it in a different kind of way when you're dealing from a chart like this. And probably part of it is just because this is actually coming from real data, and whereas when you're doing something like that, what you're talking about is theoretical. I don't know. That's about the best I can put it. But if you still got questions at the end,
I'm gonna save them for the end. Just
so
we can do everything.
I finished up earlier last night, and so.
Well, thank you so much. You kind of explained that, and I kind of see it now. I just have to go practice it and see if I understand it. But thank you.
Okay. All right. So to finish up chapter 4, it's 4.4 is called the counting principle, permutations, and combinations. Now, counting principle and permutations are really pretty much the same thing. It's just that. So we're going to start out kind of simple with what the counting principle is. And I think a lot of people are familiar with this, but it's how many different options you have if you mix multiple things together, multiple experiments. So this is just a kind of a simple scenario. Let's say you can buy a couch in 2 kinds of fabrics, either leather or microsuede. And then you can get 4 different colors, tan, white, red, and green. And there's no exclusions. They can all be mixed. So there are the fabrics. You got the leather and the microsuede, and you got 4 colors, the tan, the white, the red, and the green. Now, that little thing I've got drawn there is called a tree diagram. And that's very useful to help you see for small situations like this. You can't do this with everything. And then the next problem after we deal with the couch thing here, we'll see how it works a little bit differently. You don't need to see them all, but this kind of helps you to see, because you've got 2 fabrics, 2 colors. So 2 times 4 means there's 8 unique sofas there. So you got the tan leather, the white leather, the red leather, the green leather, the tan microsuede, the white microsuede, the red microsuede, and the green microsuede. That's 8 of them. Now let's say we throw in one more option there, because it doesn't just work with 2 experiments. We can throw in another one. Let's say now you've got the option of either having a recliner in that sofa or not. All right, and that's what this little yes, no means down here. And notice that what it's doing for every one of those color selections, you've now got 2 branching off of that, yes and a no. And see, and you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Well, like I said, we don't necessarily need to see them all and count them one by one, because when the numbers get big, that's not very helpful. All right. So what we're going to do is, since there's just 2 options for a recliner or not, yes or no, is what way they've got it written there. Then you multiply the 2 times the 4 times 2. So that means there would be 16 different options. And then the little tree is just a way to kind of help visualize it. So this thing can be used in all kinds of things. I mean, I've seen plenty of examples like this. But it's just, if you've got pulling from different groups and you're combining them, how many different ways can you do it? Well, believe it or not, the counting principle is what makes license plates possible, because license plates are unique, as we hopefully all know, because if any of them are the same, then that's not good. If somebody gets their picture taken by a ticket cam, if there's more than one of the same type of same number on the license plate, that's not good. So the way it works in Louisiana, and this one might be a little bit old, but there's different ones but they all follow the same pattern. We got 3 letters, and 3 numbers. All right. Now, believe it or not, the way that we can find out how many possible license plates there are with this kind of configuration, we can do with this counting principle. And it's based upon multiplication. And it really roots off of that multiplication rule in a sense. Except we're just talking about the number of ways to do things. We're not really talking about probability, at least not yet. Now, how many unique license plates can the Louisiana tag system accommodate? Well, look at this. Think about this one right here. Right there, there's just an S, but we're thinking that you can have anything from A to Z there. So there's 26 possibilities in that same spot. So that's why I have 26 right there. Same thing for this letter. There's 26 there. And U, the one there's another 26. Now, there's no stipulation about repetitions, because I've probably even seen some of these where you have BBB or CCC or something like that. They may go through and strike exclusions on certain things if the state thinks they're offensive or whatnot. But anyway, we're just kind of playing like there are no exclusions. So then that's 26 times 26 times 26. Now over here on the number side, there's 0 through 9, which is actually 10 numbers there, 10 numbers. So each one of these spots gives 10 possible. So now if you multiply all those up, 26 times 26 times 26, and then the 10, 10, 10 just adds 3 zeros. That means that there are 17,576,000 possible license plates that are unique. All right. And that's more than enough to handle Louisiana, because Louisiana is, I don't know, it's got less than half of that for population. I think it's maybe even be closer to a third of that. I can't even remember what it is offhand, 7 or 8 million or something like that. So if you didn't want to if you didn't want, and the thing about this thing is this can apply to phone numbers, this applies to passwords. There's all different ways to do it. And if you've wondered why, and this has happened in the last 5 or 10 years, whenever you got to change your password, you got to put one letter in there, one special character, and one capital, one number. Well, what that does, each time they specify one of those strange things, and not just any combination of letters, that brings in a whole different 26. For example, there's 26 capital letters, there's 26 small letters, and if the password is case sensitive, then that all of a sudden doubles the number of combinations. So all of these companies that have logins, they're worried about people about being responsible for information being stolen, so they enforce strong password codes. Now that brings up other problems, but because usually what ends up happening is people end up just writing, they have to write these things down. They're so complicated, or they repeat them a lot. But still, that's the idea, to make them as complex as can be so that people can't find them. Now, this is what's called a permutation in actuality, even though the basic underlying principle is the counting principle, that a permutation is any ordered arrangements a given set of objects. And I said that's the same thing as a phone number or a license plate, password type of thing, because order is important here, okay? In other words, STU is totally different from UTS or TUS or SUT. Those are all unique when we're talking about a permutation, because order is important. So there's something, a true permutation here, though, is just an ordered arrangement of indistinct objects. And you may have seen this thing on your calculator here. I got it down here somewhere. I'll show you on the calculator, because it's buried on most scientific calculators, or at least the old type where you just had one, set of keys. It's pretty easy to find, even though I don't know how many people use it. But that N exclamation is called factorial. And what that does, if you didn't know, is that if whatever that number you put in and then you hit the exclamation point, then it starts with that number, then subtracts 1 and multiplies, and then subtracts 1 and multiplies, and it goes all the way down to 1, and then multiplies all of those. So let me show you what I'm talking about. So let's say you got 5 people that are going to be in a race, and how many different ways can they finish that race? Well, that's a straight permutation factorial problem, because there's only one person that can finish in each spot. Nobody can take up 2, and that's what makes it a true permutation. But anyway, so that's 5 factorial. In other words, when before anybody crosses the finish line, there's 5 different choices of who could get first place. So once that person is selected for first place, there's 4 left for second place. That's what that 4 represents. And these are just multiplications. I just couldn't find a good way to put a dot in there. And then after second place is determined, then there's 3 left. Then once the third place person is in, then there's 2 spots left. When somebody gets 4th place, then that last person bringing up the rear is going to be in 5th place. So that's why that works. So 5 factorial is just 5 times 4 times 3 times 2 times 1, which is 120. So that means there's 120 different ways that those 5 people could finish the race. And every now and then I'll hear from students about something that they figured out. And I think that, I don't know if this is one that I heard from a student, but like Chipotle, like you can pick different things and put them together. Well, how many different, burritos can you have, because you can pick this, 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 and this. And once you mix them, you can find out that there's an awful lot of them if you got different choices. All right, let's take it up a notch here and just talk about, we're going to have a race again, but we got 10 people. And we're only going to be worried about 3 of them because the first 3 finishers are going to get a medal, a gold, a silver, or bronze. So how can we do this? Well, think about it a bit. It's not going to be 10 factorial because we're not worried about 7 of the people. We're going to be worried about 3 of the people. So for the first place finisher, that means there's 10 people out there that could get that spot. So that's why we have that 10 there. On the second, once the first place finisher is taken care of, there's 9 left for second place. And then for the third place finisher, there's 8 left. And if you multiply, they get those 720. Now, there's really a little bit easier way to do this, especially if you do it on a calculator. Because if you think about that second one, number 2, you've got 3 people out of 10 that you want to select. So we're going to we got a bag of 10 people, 10 names on it, and we're going to go in there and select 3 at random. Well, how many different ways can that be done if order is important? Because remember, order is important here because those metals are one is more desirable than the other. All right, they're ordered arrangements. So that's what this formula looks like. And it's kind of wicked looking, but it's not that bad. And I will show you where they're all on the calculator. They're buried. But anyway, this is just called a permutation when selecting R objects from N objects. In other words, R is the handful you're pulling out of the big group of N. And the reason why we're using R as N is just this can hold for any value. And of course, the R is never going to be larger than the N. And then if the R and the N are the same size, there's only one way to do it. But, if the smaller coming out of that larger, there's always going to be more than one way of doing it. And order is important because, as we said, is with this group, then it's important. Now, I can't really do this, so I'm going to go over to the board because this thing that I'm going to show you that formula, how it works. And I really need to do it over here by hand. It's not easy to I shouldn't have started with red, but all right, what we're doing is we had 10 people to select from, and we wanted to select 3 of them. All right, now just kind of remember the formula. Go back over there if you need to. But what it works is this number here, the largest one, is going to go up here, but it's not just a 10, it's a 10 factorial. All right, 10 factorial. And I'm going to kind of show you a quick way to do it by hand. And it's almost as quick as the calculator, but not quite. But I'm going to explain why it works this way. And then down here is 10 minus 3. And we'll look back at that so you can see. So there's that formula we're using. And I'll just go through it just real briefly before we go over there and work. See, the large number goes up there with a factorial, and the denominator is just the difference between the two factorial. And it's always the smaller from the larger because you don't want a negative one down there. All right. So that means this is equal to 10 factorial over 7 factorial. All right, so what does that mean? Well, look at this. This kind of, like I said, you don't have to go through all this, and I'm going to show you kind of a shorter way in just a second. But 10 factorial, like we saw, was 10 times 9 times 8. I'm going to come back and put the dots in there. Because these are being multiplied, because that's the definition of a factorial. And then down here, it's just 7 factorial. It's 7, 6, 5, 4. All right, so now so all of these are being multiplied, and that's important because if you think back to the idea of a fraction, like if you have 4 over 12. Well, the reason why this reduces to down to 1/3 is because you got 4 times 1 and 4 times 3. All right. And so the common factor of 4 reduces to 1, and you're just left with 1/3. It's just a little bit more complicated here, but the same thing is happening. 2 over 2 is 1. Well, 1 over 1 is obviously 1. 3 over 3 is obvious is 1. 4 over 4 is 1. And like I said, is you don't have to go through all this. I'm just showing you why it works so that when I do the short way, you can breathe a sigh of relief. Because all that's left here now, when you do that, notice that everything in the denominator is just 1. So this is 10 times 9 times 8, which is 90 times 8. I think it's 720. Double check me on that. All right, now let me just show you a shorter way. And like I said, if you do it the short way, it's almost as quick as the calculator. So instead of expanding out the 7 factorial, the smaller one at the bottom, I'm just going to leave it as 7 factorial. But what I'm going to do with this one is, and you can kind of see here, that right there was the same as the one on the bottom. So I'm just going to go down 10 times 9 times 8 times 7 factorial. And then I can just take it all out there now. That's 1. And all I've got left is the 10 times 9 times 8. Same thing. There's a neat little video I got in the notes that you can watch. But it's something we need to, once we finish the whole lesson today on chapter 4, it'll make more sense if you want to watch it, because there's another thing that's similarly related to this that's called combinations, and that kind of helps you understand the difference if you want to. All right, so let's say let me bring up the old Wabbit Emu thing and see if we can see where the calculator is at to do this. Well, it's not cooperating, or it's just slow. What I may do is just do the next couple of things, and then we'll look at that all at once, because we've looked at two of the things you can do with the calculator, and then we'll look at one more, and then they're all in the same spot. And I've actually got a screen print. A screen print of the. All right. Well, let's do one more of these. By hand, and then like I said, yes, and then I'll show you the combinations, and I'll show you where they're at in the calculator. I don't know why it's not. Calculator's not coming up. Oh, there it is. All right. Well, like I said, I'll just finish this one little section up, and then we'll look. Now, I got this one. It says, out of 17 contacts in her cell phone, how many different ways can Shanna set the first 4 speed dial contacts? Okay, when it says how many different ways, it means that she's concerned about the order there. All right. So our two main numbers are 17 and 4. And now let's go and do that. And I'll do it the quick way. So then 17 factorial goes up here. 17 minus 4 down here, which is 13. So that's 17 factorial over 13 factorial. And you just got to remember, those are not just plain old 13s or plain 17s. They're factorials. So what I'm going to do is I'm just going to go down until I match that one down there, rather than write them all out. So so these are being multiplied. So then we bunked out 13 factorial out. That's just 1 now. And we've got 17 times 16 times 15 times 14. Let's see, did that so that's 57,120. So if you got 17, it doesn't have to be just contacts. It would work no matter what you were dealing with. But if you had 17 things to pick from, and you want to arrange 4 of them with ordered, how many different ways could you do it? Well, there's 120. All right. Well, let's do this next thing called combinations, and then I'll show you how you can do all these on the calculator. Let's see. Well, it came up finally. So what you got to do is, let's see, you hit the math button, and then you go over here where it says probability, and there they are right on the top. So you got to hit that math button first, which is the third button from the top on the left. And then you got the first one, you don't need that. That's a random number. No reason to have, we need that. The fourth one is the plain old permutation. So like I said, is we had 5. Whoops. All right, you got to do it first. Okay. So 5, math. So there's the 120. So it does it all for you. Let's do that one we just did with the permutations. It was 17. So this is what you got to realize is you're putting in 2 numbers. So you got to put them in. Whoops. So what I got to do is I got to put the 17 in first, then go to the math, get that function, which was the P, and then I think we said 4, 57,120. All right, let's talk about, and this is the screen. Go back to the notes so you can see the screen. So I got it there if you need to, but like I said, you got to hit the math button first. And if you're not using the TI-84 Plus, I mean, it's not going to be in the exact same place probably, so you might have to Google what you want to do and put it in the version of the calculator you have. All right. Now, if order is not important, then we got a whole different animal. All right. And as we're going to see after we finish this problem here, we'll see one more where we kind of bring this back to probability, and you'll see that there's something very common that combinations are used for, because it kind of might not make sense that you can use combinations for anything if you're not worried about the order. And then I might just bring up this fact. A combination lock is not really a combination lock, it's a permutation lock, because combinations don't deal with order. The order is not important. And so when you're talking about putting in your combination on a combination lock, you have to get the order right. So somehow that just became a misnomer mathematically. So don't let that throw you, because like I said, there's always things like that in real life where things are misnamed. So, all right, but the combination formula is pretty much the same thing, or the combination of selecting R objects from N objects when order is not as important. It just uses the C just to show that that's going to do something slightly different. You'll notice that it's got both of the same things that the permutations have. The only thing that it has that's different is an extra R factorial factor in the denominator. And what that's effectively going to do, if order is not going to be important, you're going to divide out some of the ones you have from the permutations, and therefore you're going to have fewer combinations than you would for permutations. For example, on this, You know what I might do just to kind of show you the difference? Let's just say there's 17 faculty. And then that way it'll be the same numbers as the other ones. And maybe you'll kind of make it a little bit easier to see. So it says a committee of 4 teachers to be chosen from a faculty of 17. How many committees are possible? Now notice here, when you're talking about committees where there's no pecking order, then it's just pulling out that handful without respect to order. It's just kind of implied there. If there had been some offices here like president, vice president, secretary, and treasurer, then you would do this with permutations. But there's no order. Those people are all equal. Doesn't matter what order they're selected in. So let's go to the board and do this and see how it works out. All right. I'm going to start a new screen because this will take a little bit extra work to do it by hand. All right. So this is C 17 and 4. Now before, remember, we still got that 17 factorial up there. And we still got the 17 minus 4 factorial. But what we've got is an extra 4 factorial down here. So that's a minus. And what these are being done here, these are being multiplied, so you just got to remember that. All right. So we still got the 13 factorial down here, and I'm going to put that. And for time being, I'm going to just kind of ignore the 4 factorial. And I'm still going to do the same thing that we did before. And you can kind of remember on this page when we got it, we just ended up with 10 times 9 times 8. So I'm kind of going to speed up a little bit just to get to that. No, it wasn't this one. It was the one down here. It was the one where we had the 17, 16, 15, 14. So so we got the 13 factorial down here, which is still going to take that out. So these are still gone. Now, what we're left with is, if we're doing permutations, you remember, we just multiplied those 4, and that's where we got our 57,000. But now we got a 4 factorial down there, which is actually 4 times 2 times 3 times 2 times 1. So I'm going to write that in my next step. All right. So now, permutation and combinations will always reduce to a whole number. There are fractions here now, but they'll always reduce to a whole number. So you'll never have something like 1.5 or 3.7 or anything like that. It'll always be a whole number because what we're talking about is ways to do something. All right. So now, what that means is we can take these out. In other words, there's got to be a factor of 4 in there somewhere. There's got to be a factor of 3 in there somewhere, and there's got to be a factor of 2. The 1 doesn't really matter so much. But let me go back to the red. Now, it's pretty obvious that 4 goes into 16 4 times, so I'm going to do that one first. And that's now a 1. So I got a 4 up there instead of a 16. Which of these are divisible by 3? Well, the only one that's divisible by 3 is the 15. So 3 goes into 15 5 times. And then the only thing divisible by 2 is the 14. We could also do into the 4 again if we wanted to. But I'm going to do the 17. So 2. So now what we have is 17 times 4. And I'm going to come back and put the dots. Now, when we multiply those, what do we get? $17 times 4 times 5 times 7. We get 23,080. Hold on 1 second. I want to try something. So what this ends up being is it's the factor of 4 factorial that makes a difference here. If we were to take a 4 factorial and calculate it out, it comes out to 24. 4 times 3 is 12, and 12 times 2 is 24. If we were to multiply 2380 by that 24, we would get back to the 57,000. So as I had said, is if you're having trouble understanding exactly what the difference is and what to use them, this right here essentially tells you that. There's a video somewhere. Where did I put it at? Oh, it's down here. Right there. So if you're curious about that and you're having trouble about when to knowing when to use them, then check out that video. All right, any questions? We're almost finished with chapter 4, and I really think 5 is kind of a breeze compared to all this, but it's a matter of interpretation, maybe.
Mr. Cruz.
Mm-hmm.
For the last example on the PowerPoint, the counting the probability, how do you know not to use the 2 burned out light bulbs? Wouldn't you have to minus that from the 8? Do you know where I'm looking at?
On chapter 4?
On chapter 4, yes, sir.
Which slide number?
I'm sorry. It's like the second to last one. I don't have the numbers on mine. It's example counting in a probability.
Yeah, that's what I was getting ready to cover, but a problem on that. Well, what was your question about this? Because I got it up now.
How do you know not to use the 2 burned out light bulbs? Wouldn't you have to subtract that from 8?
Okay, a box of light bulbs contains 8 good light bulbs and 2 burned out light bulbs. 4 is going to be selected at random to put into a new lamp. Okay.
Yeah, they added it to it, so you would just still add the burnt out light bulbs.
Okay, you're doing 2 different combinations here. Okay.
Okay.
Remember, you're doing this blind, this box, and you've got to do your denominator. You kind of gotta play like you can't see anything. So you're going in there and you're pulling out 4 out of 10. Okay.
Yes.
And then that gives you the 210 different ways to do it blindly without, in other words, some of those are not going to be getting good light bulbs. You're going to have the possibility of getting a burned out light bulb. But what you can do also is for the numerator is we're only going to pick from the good light bulbs now from the 8. So the 4 get picked from the 8. In order to be all good, we got to calculate that there's 70 different ways of doing that.
Okay.
And so then 70 over 210. And this is generally a good practice, is always to do your denominator first. Find out what that big number is, put it down there, and then look at the other one. This is a pretty good one. I was going to do a different, the reason why I was going to do a different one is just because most people don't realize that they use combinations if they play the lottery. The lottery is probability based upon combinations because you do not have to match the order. You just have to have the 4, or I'm sorry, if it's pick 5 or pick 6, you just have to have the 5 good ones, the one that match what you picked. Now, there's a whole bunch of different ways to do it, but that's kind of the one I was going to cover. If you got more questions about this one, though, that's fine, because this is a good one, too.
Okay, I would like to see your example. I feel like you're more understanding anyway.
All right, and just to make sure, let's just kind of go back over to the calculator and oops, you got to put in the number first. So we're going to put in 17, and then I'm going to go to the math probability. And this time I'll do the combinations. And then it was 4. See the 2380, you get the same thing. So there's nothing wrong with using that calculator for this. Like I said, I'm just trying to show you why. Because if I just showed you how to do everything on the calculator, probably we could finish in about 10 minutes. So, and two, I mean, I really think if you kind of use that shortcut method that I was showing you why it worked, you'll also have another way to do it and kind of just double check, see, because now I know that I did it right. I got, an agreement of answers, which is a good thing. It's a confidence builder. All right, so let's go back and look at the question that I've got about probability and winning the lottery. All right. Now, essentially what we're going to do here is we're going to handle how many different ways numbers can be picked. How many different ways numbers can be picked for the lottery. Now, they give us, I think, is 1 through 44, so that's 44 numbers. I'm trying to just see if I got anybody that's here. Hey, man, is Jose out there? I don't see him. Elizabeth Pham? I don't see. I'll check afterwards. I don't see Renee anyway. Okay. Or Megan. All right, we'll come back to that. All right, so we want to calculate 2 things here. One is just a probability of winning with 1 ticket, and then we'll see how buying 2,000 tickets. All right, I can't remember which one you asked me about. Jamal, did you send it through Ask Your Teacher or something? I know I had several of them that I replied to, but I didn't remember yours. Sometimes things get lost, and I don't like people to think I'm ignoring them. It's just if I get them. All right. So just like what I showed you on that one that you had on the PowerPoint, we want to find out how many different ways there are that possible to pick 6 from 44. Well, since this is a combination, because we're not worried about, and most people know this, you don't have to worry about the order that those numbers come out of that popcorn machine on Saturday night or whenever they pick them. You just have to have those numbers in some order, because if you had to pick them in order, nobody would ever win. Because you saw on that last one, that was a factor of 24 difference, and it made a big difference in the number of ways. So the first thing is going to be all right. Maybe you asked it further on up. I don't know. I hope I didn't miss something. I don't see anything on here. All right. So we're going to do that first. So that's, like I said, that's the all right. Rather than go through it, let's use that calculator to make it quick, because I want to do one more thing before the break. The 4.4 stuff. So let's just do this with the calculator. Oops, you got to put in the number, the big number first. All right, so we got 7 million. So we just put in there comma so we can see it. That's actually a 2 there. Did it and then somehow erased it. So that's 7,059,052. All right, now, if you're just buying one ticket, that means you're picking just one of those. You just got one. One over 7,059,052. All right, because there's just gonna be one. You just got one hat in the ring. But if you got 2,000, well, we're going to multiply this whole thing by 2,000. Now it's 20,000 over 2,000 over 1, so it's just the 1 that gets multiplied. Now, the one that you had from the PowerPoint, Holly, I mean, that one it comes out nicer because the numbers are smaller. These are going to be incredibly small values, and as I remember, let's say I'm going to approximate these as decimals. I'm not even sure I'm going to have enough room over here, but I'll try to squeeze it in there, and I'll show you the difference. Because it's really hard to see as a fraction, and that's why sometimes they want you to do as a decimal. So this ends up being let me put it up here because I'm going to need some extra space. It's a long value because you got 6 zeros. And then it's like 1417. So you can see that's pretty small probability decimal wise. It's hard to see that as a fraction, but if we take that and multiply it by 2000, all right, let me just do it on this calculator. So now it's more reasonable. It's got 3 zeros.
How are you getting the 0.000? How did you get that?
You divide 1 by 7,559,052.
I don't know why I'm not getting that.
What happens when you divide? You can see it here. Let me show you on the calculator.
I'm getting 1.416620815 negative 7. I don't know how I'm getting that.
Okay, well, this is why using calculators are a bad idea. And I mean, that's why most of my teaching career, I've tried to do things by hand, because this is the problem with calculators. And it's a universal problem with calculators. What does that mean? Because that's what I got too. What does that mean?
I don't know.
Yeah, that's the problem. And I see this over and over. That's scientific notation. Because they can't easily, if you've got a bunch of zeros, they're not necessarily going to be able to fit them in there. So after you hit about 3 zeros, they put it in scientific notation. So you have to know, if you're using a calculator, you've got the possibility of scientific notation. All right?
Okay.
And that's what those mean. This means that top one. That means you got that negative 7 means you got to add 7 decimal places to going to the right. This means you got to add 4 decimal places going to the right. If these were positive, then that means you got to add that many decimal places going to the left. I'm sorry, I just said it just the opposite. You got to, for the negative, you got to add the decimal places going to the left, and for the right, you got to go to the right for the positive numbers.
Okay.
But that's scientific notation. But I run across this all the time, and like I said, that's the way all calculators do that, all scientific calculators, because if you've got a big number, a small number, I don't know necessarily what the convention is on doing that, but it's usually because they don't want to just fill up the screen with a bunch of zeros. They want you to see the accuracy of it. So that's what that is. That's scientific notation. There's nothing wrong with it. It's the same thing. Oops. So I'll just finish this one, and then hopefully you can see. But that's the same thing. That's what these mean as decimals. See, that's this one, and that one is this one. See, and they just put it in scientific notation on the calculator. But if you have to put it into a text box for an answer, you got to put it in like this. They'll say round it off. I can't remember if they have any. I don't think they have any of these that small. So if they do, just remember that. But I just remember last semester, like we were getting ready to go on that lockdown thing, and I was telling people I was giving them the last midterm exam in a room on electronics. It was on the computer, and I remember asking them. I said, "Look, you got any questions? Ask me. I want to help y'all because I know this is a lot of pressure going on." And I remember there were a couple of people that they had problems and they couldn't remember what that meant. But that's scientific notation. So like I said, calculators don't solve all your problems. That's the drawback of calculators. There are some things, and like I said, if it were me, I would be doing the whole thing with like a spreadsheet, but there are some things that are probably easier with calculators. But all right, let's finish. That finishes up chapter 4. And I'm going to just go over 5.1 pretty quick, because 5.1 is really just a recap of basic principles. But the reason why they make this thing that seems like it's kind of long is the fact that when you're talking about discrete probability, you're only going to be working with a finite number of whole number values for outcomes. Whereas if you got infinite, which is what continuous data is, it's really hard to see the outcomes. So like I said, they take this, oops. Oh, I know what, I wanted to go to the PowerPoint, not on the notes. I got this in the notes, but again, this is one thing that's kind of a bit crazy in the book, because like I said, this is one of those things that's kind of book peculiar, I guess you could say. But remember what discrete means? It just means whole numbers. Now, random variables is just like a variable in algebra. It just that when we're talking about a random variable, it just means that we don't know what the outcome is going to be. When we roll a die, we don't know whether it's going to come up 1, 2, 3, 4, 5, or 6. We just know it's going to come up one of those numbers, and each one of those has a probability of 1/6. Well, that's what a random variable is, just so you know. Again, this is almost just handling definitions of things. All right, it's nothing new for the most part. So remember, discrete values are ones that are whole numbers. And they give an example: the roll of a die, the number of siblings a person has. Now, continuous variables, if you're talking about heights, you can look on a measuring tape or a ruler. Between 1 and 2, there's at least 32, or is it 16? I think it's 30 seconds they go down to on a ruler. So if you're measuring the length of something, you can go down onto a ruler 30, have 32 different values between 1 and 2. If you give when we save whatever that question you have, Elizabeth. Like I said, I don't know if I missed something or what. I don't see any kind of questions in there. But anyway, so we're only going to be concerned about discrete random variables here, because it's really, because dealing with continuous variables is going to be very, very complicated. So we're just talking about discrete things, and we're looking at the same properties. Okay. And these are the same things. Maybe they looked a little bit different in chapter 4, but all this just means is that a probability is always a value between 0 and 1 inclusive. It can be as small as 0 and large as 1. That's all that's saying. And then the other thing is the sum of all probabilities for an experiment have to add up to 1. That's the reason the complement rule works. All right. Now, if we're talking about discrete probabilities, see, we can list all those different outcomes. Whereas if it were a continuous, you're not necessarily going to be able to do that, or it's going to make it very, very complicated if you've got tons and tons of outcomes. But these are just what we call discrete outcomes. They don't have to be positive, but these are just very simple ones: 1, 2, 3, and 4. And then these over here are intended to be the probabilities for each of those outcomes. Now pay attention, because this is one of the things they harp on when they're dealing with, exams and stuff. Like I said, is from these tables. Now they ask, does the following represent a probability distribution? And the reason why they showed you these rules is because they want to know, do these things add up to 1? All of the probabilities, not the numbers, the outcomes. And is each one of the probabilities between 0 and 1? Well, 0.25 is fine probability. 0.65 is a fine probability. But that negative probability is something that can never happen. Probability is always no less than 0, no greater than 1. So because of that, this thing is not a valid probability distribution. All right. Here's one. Now over here, it's fine if these things, these outcomes are, negative. That doesn't matter. Now, it kind of irks me that they put in the 0.5, but let's just look at it like that, because then that way they're discrete. But it doesn't really matter what these are. Those can be positive or negative. They can be any values. But what we're looking at here, are all these probabilities viable ones? Well, 0.17, that's 17%. 0.25 is 25%. 0.31 is 31%. 0.22 is 22%. 0.05 is 5%. And if that's the case, that all of them are viable probabilities, and they add up to 1, and you can see that they do, just take them and start adding up. 0.17 plus 0.2. I don't know why the calculator goes off. What do they think? It's going to run down the batteries? So 0.25 and 17 is 0.42 plus 0.31 is 0.73 plus 0.22 and then plus 0.05. So all of these add up to 1, okay? So this is a fine probability distribution. So all this is doing is just checking to see if you recognize these two principles, which are from chapter 4. And the two principles are that there's no negative probabilities or no probabilities greater than 1, and that all of the probabilities add up to 1. Now see the problem with this one, you look at the first outcome of 1, you've already got a probability that's greater than 1, so this thing is not valid. Now, as I said, there's really nothing new here, because they give us this little probability distribution, and this is dealing with 4 patients. They go and get their blood pressure checked, and this says how many different, how many of them have high blood pressure. Well, they could either have 0 of them, none of them have high blood pressure, 1 of them have high blood pressure, 2 of them, 3 of them, or 4 of them. And then they give us the probabilities over here. And if you add up all those, they all add up to 1. But all they're asking is find the probability of 2 or 3 and remember, that's just the addition rule. So we're just going to go to these 2 and add them up. Like I said, there's nothing new here. 20.27 and 0.8. They got another question, more than 1. Now here's where you can use, so more than 1 just means 2, 3, and 4. You got to watch the wording. It doesn't include 1. If it said at least 1, then it would, but so it's just these 3, so you add them up. And it's 0.36. Like I said, they're not really giving you a different rule. You're just doing it from a little chart. And like I said, they can give you a little chart because it's discrete. here's one that says at least one. Well, that means all four of these. Now, you could add up all four of these, and it should be the same as what they're giving you. Because oftentimes when you do at least one, it's less work to go and find none and then just subtract from one. But if you went and added those other four that are at least one, you're going to get 0.77, because one of the properties of a distribution, probability distribution, is they all have to add up to one. All right, let's and as I said, and I've tried to harp on this when we were getting in chapter 3 and chapter 4, that relative frequency, proportion, and probability are all the same things. So therefore, you can take a probability distribution and create a histogram with it. And this is what it would look like. The only thing that's different is the vertical axis is probability. It's measured as probability. This is the same thing that was in chapter 2 when we were asked to calculate a mean from a frequency distribution, except it's easier because there you had to figure out a midpoint. Well, here with the probability distribution, these values are already set for you. You don't have to find a midpoint. So to find the mean, you just multiply across and add them up. Let's see, so I'm going to show you. So that would be 0, oops, plus 0.5 or 0.5. So let you see what they're doing. So if you add all those up, you get 1.2. So again, it's the same thing as what you did with that frequency distribution when you wanted to find the mean directly. But this thing also has a different name. It can be called expected value. And it's really very similar. It's just a matter of multiplying across. This is really the last thing we need to look at, and then we'll take a break. I know I'm running a little bit late. I just got long-winded. But believe it or not, probability can be used in other kind of situations than just, games of chance. The way that they set insurance rates is actually based upon probability. This is an example of something that a mineral economist has put together. And, this could be easily applied to something like oil fields or what around here. But there are 3 different outcomes they give you here. They say that when they go out to drill or do this mining venture, we could either lose negative $30 million. I'm sorry, lose $30 million, which is why it's negative. We could get $20 million, or we could get $40 million. So what this is intended to do is find out whether these scenarios are good or bad. In other words, do we want to take this risk? Well, the way we do it, we just calculate that same way we calculate that mean, except it's called expected value. So negative 30, in other words, these 3 are the outcomes here, and these are the probabilities. So the negative 30 times 0.4, which is so that comes out to 12 negative. And then we got 20 times 0.5, which is 4, I believe. No, I'm sorry, that's 10, because that's half. And then 40 times 0.1 is 4, I believe. 4. So 4 plus -2 is 2. So what this essentially means is, and it's not just on one venture that expected value is based upon. It's just like everything else, like the roulette wheel. The house has figured out what the expected value is for them over time, and I could almost guarantee you that it's going to be positive in their favor. So they've got it essentially rigged, so they know that as people play more and more, there's going to be a positive expected value for them. That doesn't mean people can't win, and this is why, if you've seen any of these shows about gamblers that figured out how to change the odds in blackjack, they eventually will get banned because the house doesn't want them doing that. Because if they start if that gets encouraged, then that shaves off their positive expected value and can make it negative. All right, so let's take a break, and then we'll come back. And like I said, I don't really think 5.2 is that bad if you just think about it with a calculator. I will try to explain it to you. Let's try to take 10. Like I said, I'm a little bit later than I wanted to be, but I'll stay around afterwards. As I said, I just wanted to get it onto the recording, but chapter 2, when you had to figure out the means, standard deviations from the calculator by just entering the 2 columns of data, and our stats, right? The same thing you use for everything. All right, folks, let's finish this thing up. And on Tuesday, you'll have, that'll be like a work day. Bring in any questions you got. I've put in the modules that little study guide thing about the things that are important to carry out of this. So you can look at that. And then, like I said, I'm not going to have any more new material to give you on Tuesday, but that test will be active. And you will have to, so that day will be, when the heat is on. Now, the bad thing is, let's see. Let me look at that calendar again. I was just noticing last night that I'd had the 29th as the final day for that test. So I realized that that doesn't work so well for you folks. So I extended it through the 30th. Now, the reason for that is because Wednesday the 1st is that's the deadline for me to enter midterm grades, and I really think it would be in your best interest to have 2 test grades in there for that. I mean, the midterm grade isn't binding or anything like that, but it just kind of gives you an idea of how well you're doing. So that's why I got that. Now, I usually would. The reason why I wanted it to end on the 29th originally is so that way I'd have the 30th to do the calculations on the grades. But I could probably do those on Wednesday morning. So that's why I can give you that extra time. I might even be able to give you like 6 hours more as long as they're in like 6 o'clock in the morning. But you can let me know about that next Tuesday. All right, so let's look at this binomial distribution. Now, this thing, probably the hardest thing about it is just realizing that it's very intense to do it by hand. Now, but one of the things what binomial means, it means that there's only 2 outcomes. It's like the coin flip. You're only going to have win or lose. There's no in between. There's no other values.
Excuse me, Mr. Cruz. Are you going to do objective 6, or did you already do that?
What was objective 6?
This variance and standard deviation.
Well, that's what I just added about the calculator. I mean, it's the same thing as the frequency distribution, and you can throw it in the calculator. I went ahead during the break and just recorded that, but it's essentially the same thing as the frequency distribution, both the mean. You can put those in the calculator in those 2 columns and do them like that. It's just the benefit of doing of this is of the probability distributions. You don't have to find a midpoint like you did in that other thing. And there's no mode or there's no mode or median either. So, but like I said, I went ahead and recorded and put it in there. But I don't know if you got here, but after I started. But next Tuesday will be a work day, so bring anything in and we'll work. Handle anything at that time. But this thing, like I said, it's really not that tough, especially if you just realize that doing it by hand is incredibly intensive. And I'm going to try to show you real quickly how to do that. But the first thing you got to know is whether something is a random variable or not. Okay, a binomial. I mean, in other words, you can only have 2 outcomes. So this is a good example about this fast food restaurant and they've got 20% of people are going to win because they'll give you a coupon with your meal and it'll say either you won a free hamburger or better luck next time. So since there's 20% of winners in there, then that would be consistent throughout. But the most important thing is yes or no. Win or lose. It's like the coin flip. Heads or tails, win or lose. They even call it success or failure. So these are the things, and I think 2 of these could be combined to make this. But what constitutes a binomial distribution? Or this book uses the term distribution, but you could also say experiment. But when it says a fixed number of trials, just like for this thing over here, it says 10 people order lunch and you want to find the probability that 3 of them win a burger. Well, that's the same thing that we're talking about here. You're doing something a certain number of times. So there were 10 trials in that burger example. And there's 2 possible outcomes. Win a burger, no burger, success or failure. The probability of success is the same on each trial. That's important. All right. In other words, you know that the probability of success is the same on that coin flip every time. But there are things that might be sort of binomial. But if the probability of success changes, then that's a problem. And I'll show you an example of that where that happens in a second. And these things are pretty much the same thing for all intensive purposes, but the trials are independent. And so what that essentially means is when you flip that coin and you get ahead, then on the next time that you flip, the same probability exists of getting ahead. It doesn't get reduced by taking one head out of the mix. And I'll show you again what I'm talking about. And then X just is what that represents is the number of successes that you want. Say a fair coin is tossed 10 times. Let X be the number of times the coin lands on heads. Is this a binomial experiment? Well, each coin toss is a trial. So we got 10 times. 2 possible outcomes, heads and tails. And X we'll just record the number of successes. So yeah, this is binomial experiment because one coin toss is independent from the other. Now they give you this one, and this is a good example because before the coronavirus thing, I was watching basketball, and I guess I had never thought about this, but basketball players are not all equal when it comes to free throws. All right. Some of them are very good at making free throws, like 80%, and some are like 30%, folks. Now, they say 5 basketball players each attempt a free throw. Let X be the number of free throws made. And then they're asking, is this a binomial experiment? Well, it's not, because if you've got 5 different players, their probability of success is going to change because it's very varied. But if you took the same player, if we wanted to fix this, and had them throw 5 free throws, then that would essentially fix the issue. All right. So here's the last little thing. It's just kind of tedious because I always got to tell you the whys. All right. Now, as I said, is for most of chapter 5, you're not really dealing with any probabilities any different. You're still dealing with or and probability throughout. In 5.1, we just looked at some little or probabilities. We just added. We didn't really do any ands. But with the binomial probability distribution, we could do it using all of those probability formulas that we learned, the or and the and. But let's say we've got a binomial experiment here. We're going to toss a coin 3 times. And this is not just any coin. It's a biased coin. And that's all right because it's going to be consistent. We're going to use the same coin that's biased. And then they say 0.6 of the time it comes up heads. And the reason why they're doing this is it's just if they use 0.5 and 0.5, it might get a little confusing. So they're making the probabilities different. So if we want to compute this, the probability of getting 2 out of those 3 flips, how can we do it? Well, here's the 3 different things that could happen to win this or to get 2 heads. You could either have head, head, tails, head, tail, head, or tail, head, head. Now, there's a bunch of other combinations that could come out, but these are only 3 that are going to give you 2 heads. Because you could have tail, tail, tail. You could have tail, tail, head. You could have head, tail, tail. You could have, say, what is it? There's 5 other ones, actually, that would not have 2 heads in it. But these are the 3. Now, watch this, because this is the multiplication principle. Now, the probability of a head, and a tail looks like this. All right? 0.6, because that's a head. 0.6 is a head, and then the 1 tail is the 0.4. Now, instead of writing it so long way, we're gonna, if we write it, we're using a shortcut, a simplified form. We could just say 0.6 squared. All right, and then you could even say that this is 0.4 to the first power if we wanted to. Now, the other 2 are essentially the same thing. No matter the arrangement, you're still going to have 2 0.6s in there, whether the 0.6 comes first, second, or first and third, or second and third. So both of the other 2 could be written in that same way. So there's 3 different ways that can happen. So in essence, if we take and multiply just one of those by 3, instead of just multiplying them each separately and then adding them up, that's the same number. We can just multiply by 3. Well, that's the addition rule, essentially. So you're using both of those things in here. Well, what we're doing to get that 3 is we're essentially taking combinations of 2 out of 3, where 2 is the x and n is the 3. And if we did that, that's what would make this. And then this part is just the probability of success to the power of how many successes we want. And this is the probability of failure to the power of how many losers we can have, how many tails. So look at this. This is how this formula can be built in that very simple case. But we don't want to have to do that with anything more complicated, because if it were larger numbers for the number of trials, it would get awful big. So you don't even need to necessarily remember this formula here, because none of the formulas you have to do that with in this class. But this is what this is. This is the combinations. In that example we just looked at, we're pulling 2 from 3 using combinations. The order doesn't matter. The probability of success, P is always the probability of success. That's 0.6 to the second power. And then the way we got the 0.4 is 1 minus 0.6. That's 0.4. And then n minus x was 3 minus 2, so that would be the 1. And then you would just have it for however many you did. And you remember there were 3 of them, 0, 1, and 2. Well, let's just look at an example. And like I said, I'm going to show you real quickly how the by hand works. And then we'll jump over to the calculator and see that it's real easy over there. All right, here's what we got. We got the Pew Research Center reported in a recent year that approximately 30% of U.S. adults own a tablet computer such as iPad, Samsung Galaxy Tab, or Kindle Fire. So suppose a simple random sample of 15 people is taken. That's our number of trials. That's N. And then we want to use the probability distribution, the binomial probability distribution, to find the following. All right. So I'm going to write over here on the board what we know and what's important. All right. So the probability is 0.3. That's the 30%. And we know that N, which is the number of trials, was 15. That was what it was, wasn't it? 15. All right, so for A, we wanted to find X is equal to 4. Because, let me just write these down and then I'll go back. We'll go through them, and then, like I said, then I'm going to show you a couple of different ways that you can do these, but I'm going to concentrate on the calculator. All right, so let's go back over here and just look at each one of those in kind of detail. And you can see how those come about. All right, so the first one was, I wish I could do a split screen on this. I don't know how to do that yet. So the first one, A, is find the probability that exactly 4 of the sample people own a calculator. That's why I have X is equal to 4. That's a real simple calculation, almost even by hand. But here's where these other ones get difficult, and this is why you got to have some kind of technology. Find the probability that fewer than 3 of the people own a tablet. Fewer than 3 was X was less than 3. So that means 0, 1, and 2. C is find the probability that more than one person. So that's more than one person. That's like 2, 3, 4, 5, 6, 7, 8, all the way up to 15. And then the last one is find the probability that the number of people who own a computer or tablet is between 1 and 4 exclusive. All right, so let's go through, and I'll just kind of show you how beleaguered this could get you if you do the by hand. So doing 1 is not so bad, because when we say exactly 4, it's sort of like that little one example we went to when we said we want exactly 2 heads. Well, look at how you set it up. You got the 0.3, and then your x is 4. So you got the power to the 0.4, and then this is 1 minus 0.3, which ends up being 0.7, and then 15 minus 4 means 11. So this means you want to find the probability that 4 have a tablet and 11 don't. This is the probability of a tablet. This is the probability of not having one. And then the number of ways this can be done is that combination thing. Well, going through all that is 1,365, and they don't tell us what these are, but when they all multiply, it comes out to 0.219. Now, look over here. As I said, is fewer than 3 means 0, 1, and 2. So look what you got to do. You got to do 3 of them. A lot of work. If you do more than 1, there's a long way and a short way to do it. If you do more than 1, you could do them individually and do 2, 3, 4, 5, 6, 7, 8, 9, and 10. Or you could do 0 and 1 and then do the complement rule, which is what they're doing there. And then for this one, you could just, because it said between 1 and 4 exclusive, so that would be just 4 of them. Now, just as a side note, there's tables where you can do this. They're in the back of the book, and this is, I don't know when they started doing this, probably in the 60s and 70s, because what they had at that point was they had computers that could calculate these, and then they would just put them in the tables. The drawback is your probability may not be up here, but they just show you, and you just notice that if n is 15, and this is what you would look up first. You look up that n, and then find the x, 4, and then go over your probability, and there it is. That matches the other one. But let's do it with the calculator, because the table does make it a little bit easier, because you can just pull the values out. The drawback is they're not going to be as accurate as calculator, or even by hand for that matter. But see, there's a lot of work left out when you just use the table to figure out for you. See, for example, for 0, 1, and 2, you just find those 3 there that represent 0, 1, and 2, and then add them up. All right, so this is where the calculator comes in, and we'll do each one of these with the calculator. So this is, oops, I gotta show it to you. This is something weird here. Let me fix this before I move on. Why did I put that right there? That's supposed to be a less than sign, because it said inclusive. All right, so let's go back over and look at that calculator. All right. So now the first one was exactly 4. Now you got to hit second, and then you hit that thing that says vars, and then you scroll down. Number 2 we'll use in chapter 6. Actually, a lot of these will be used in chapter 6. But you go down, and there's 10 of them, and then you got one. They start over with A and B. And then there's the binomial PDF and the binomial CDF. Well, this is important, because binomial PDF just means probability to density function. And when you use that one is only when you have exactly one value. Like I said, you could do all of these with exactly one value, but it's a pain in the neck. You still got to add things up. But PDF, so for the one that said exactly 4, let's do that one. Oops. This is really pretty easy. Put that enter. So there were 15 trials. The probability was 0.3. That's that 30% they gave us. And we wanted to know the probability for exactly 4. Look at that, 0.28186. Now, the rounded off version was 0.2819, because those tables are only accurate out to 3 decimal places, and evidently that's what they were rounding off for with their calculations. But notice, PDF, that's one value. So let me go back over to the board. So this would be I'm going to go out to 4. Just watch what they ask for. I think they're probably going to ask 3. All right. So this is a binomial PDF. All right. And the key function, the key, it's a D. But the big thing that's the difference is a P there. That's the one we only do one value. X is one value. Now these other ones, like I said, is you could do them all with the PDF, but then you'd have to write them down and store them somewhere and add them up, which kind of defeats the purpose. All right, now less than 3. That means, and I'm going to write them out here, that means X is equal to 0, 1, and 2. All right, now we could either use the PDF and find out those 3 separately and add them up. But that's what this CDF is for. CDF. All right, so pay attention on this, because those things are, very much different. We still go to that vars. And then instead of the PDF, we're going to use CDF. Still 15. Probability is still 0.3. That part's the same. For the individual A, B, C, and D, what's changing is just the X values. All right. Now, the way CDF works is it's doing everything from left to right and adding them up for you. But it's only doing left to right. And in whatever you put there in that X value spot, it's going to count that one. So it said less than 3. So that does not mean it includes 3. It means that 2 is the first one, because it's going to the left. It said less than 3. Less than 3. So there's 0, 1, and 2, but this one is not going to have, it's going to do them all for you at the same time. 0.2618. Oh. What is it? No, it's 0.128. What did I say? But that's the exact same thing they got here on the PowerPoints. See that? I mean, this was from the table, and sometimes the table won't be as accurate, but in this case, they are, okay? All right, now here's where we got to watch out on the third one, because you could do them individually, but there would be a lot of them to do, because it says fewer, 1 or fewer. All right, no, I'm sorry. More than 1. So since I've Holly, you'd asked about that question. Let me put this over here. All right. Because this, you asked about the complements when dealing with this. So I'm going to do this because I actually, last night, I gotten that question from you. And I was thinking you were in that class last night, and I did this in that class about the complements. So if 1 is right here, now, like I said, these are going to keep on going on and on up to 15. Just don't have enough room to put it. But over here, we got 0. All right. So greater than 1 means these values starting here. Because greater than 1 does not include 1. So therefore, the complement is 1 and 0. I got a line arrow there. You don't really need to have the arrow on there. Let me take that off. Just going to go up to 0 because this is not an infinite number line. It ends to 0. So this is the complement. So let's just say this is A, then this is A complement. So it's a lot easier to just figure out what's to the left and find out the complement and just do these two values. And as a matter of fact, we don't even have to do those two values. We got that CDF. But the CDF always just takes the number you give it and does all the way to the left. But these are the ones we want. So we got to do that complement rule. So what I'm going to do, I'm going to put 1 minus, and then I'm going to put in this binomial CDF.
We can't see the calculator.
Oh, okay, thanks. Yeah, it's okay. So let me back up here then, because I want you to see that. I'm gonna get this. All right. I guess I might have just turn the darn thing off and back on. Okay, there we go. So what we got to do in using the complement rule, we're going to take 1 and we're going to subtract from it whatever that is. And as I said, once we found out the complement, we're just going to put in that whole number value. It's still 15. The probability is still 0.3. For all of those problems, that's the same. And then we're going to put 1 here because it's going to calculate 1 and 0 for us and then subtract from 1. So 0.9647432. All right, there's one more. Now, like I said, as you can kind of see, they did the same thing. What happened? I hit the wrong button there. So just look, so you can see the agreement. Now what's going on? I hope it's not. I want to give you all time. Oh boy. All right. All right. So I'm going to write that in there. It was 0.964. And then let's go back over to the to see it. Like I said, they did it just with the table, but it's the same procedure. It's 1 minus these two, because the calculator, the CDF, is always going to do how many you give it that number. It's going to do everything to the left. So you have to do it as a complement, or you would have to do 13 of them individually and add them up. So they did it the most expedient way. So the last one, I'm just going to show you on here. So for the last one, for part D, it was between 1 and 4. Now, that just means 1, 2, 3, and 4. Now, here's the problem. The CDF is not going to work, because if you give it 4, it's going to go all the way down and do 0 as well. So what you do to compensate is you do 4 or less, and then you do 0 separately and then whack it off. So this is what you put in. Put binomial CDF with 4, put a minus sign, then put binomial PDF again. Oh, binomial PDF they're using, right? PDF. Notice that. PDF, because they're just talking about that one value. I think binomial CDF would do the same thing in case of 0. But anyway, you put it in, and then that gives it to you. All right, so that's pretty much it. I'm sorry I kind of dropped the ball on this. I'm just getting tired out for some reason. I hate that I have to rush stuff down. It's just, just the way the summer runs, there's not a whole lot of good options, you know? I mean, I like the summer because it goes fast, but. So anyway, any questions you got now, feel free to ask. I still got some brain power left for that kind of thing. Because the presentation stuff is what kind of zaps my energy the most. So, but I don't mind answering questions. All right, so. All right. Did anybody else show up? I think we're missing one of those. I don't see. Jose, I don't see. And one of the things I told my students last night, because I got a question from one student, and they were working from behind. They were still working in chapter 3. I said, "Why are you working on that?" I said, "You really need to just, try to keep up, because as long as you're working from behind, you're never going to be up." And she was afraid that she was going to miss out on something important. I said, everybody misses out on things when they're learning. Nobody learns completely linearly and everything as they go through it the first time. So my suggestion is always get as much as you can. Then at the end of the course, you're going to have a chance you're going to have to review for everything anyway. So then that way you can come back and fill in the gaps a little bit better. I mean, and nobody learns everything. Even like the A students, they don't get everything. I mean, every once in a while I'll get somebody that might get close to it, but that's a rare thing. So anyway, I'm here. I'm going to pause this so that's got the lesson on it. But any questions you